Sorry, I have a bit of a cold, so I hope my voice isn't too distracting, but the show must go on. So we will start our investigation of circuits by looking at some simple principles of batteries, current, and Ohm's law. And here is a beautiful picture that was just too good to not include in my presentation. This is an Italian scientist by the name of Luigi Galvani. And Galvani found that you could use frogs' legs as a pretty sensitive instrument to measure electrical discharges. And at the time, the only sources of electricity were electrostatic sources. So from rubbing fur on different things, you could get electrostatic charges. And then he could measure how much electrostatic charge there was when it discharged into the frog's legs. And he was poking around, literally, and he found that if you jabbed two different types of metals into the frog legs, you could also get them to flex. So he recognized that this must be some sort of electrical discharge going on. And he decided that the source of that electrical charge must have been inside the frog's legs themselves, because when you just touch two pieces of metal, you don't get electricity. And he thought that he might have discovered the elusive life force. Now, there was another Italian scientist by the name of Alessandro Volta, and he thought that Galvani was a bit crazy, and he investigated this phenomenon a bit further and found that he could get similar currents flowing, is what they were later called, charges flowing, by inserting dissimilar metals into salt water. And so you didn't need the frog's legs, no life force, but what this led to was the invention of the battery. And we still use batteries today, but in addition to the usefulness of batteries, it was the invention of the battery that led to the invention of the electrical circuit. Before that, all you had were static charges, and you can't get a circuit with that. You need a constant source of potential difference, and that's what the battery gave us. Now, there's all kinds of different combinations of metals that will give you electrical batteries, that will give you potential differences. And Volta studied all of those, not all of them, but he studied a whole lot of them, and he came up with a list of them. And we still have all kinds of different battery chemistries today, right? We've got zinc batteries. These are kind of the typical old-fashioned AA and AAA batteries were zinc-based, and they also had carbon for one of the electrodes, so they found that you didn't always need a metal for the other electrode. We have lithium batteries, right? We have nickel metal hydride, all kinds of different battery chemistries, and most of them have pretty complicated reactions going on. This one here is pretty simple, so we'll try to use this as an example. If you have zinc and carbon in sulfuric acid, what happens is that the acid will start to eat away at the zinc, and when it does that, you get some zinc in solution here, but it's not zinc atoms that you get, it's zinc ions. Okay, and if you get a zinc ion, that means you leave 2 extra electrons for every zinc ion here on your negative terminal, so you get a negative charge here. And if you get enough of these zinc ions in solution, they're going to start pulling electrons off of the carbon. And if the carbon loses some electrons, you're going to leave it with a positive charge. Now, if this is not connected to anything, this can only happen for so long before you get enough zinc in solution that this should have been plus. There we go. Some of these zincs are going to start jumping back on, and you'll reach equilibrium where you only dissolve a tiny bit of zinc, at which point the zinc reattaching is equal to the rate of zinc being dissolved by the acid. But if you connect this to something, say a nice happy light bulb here, then the electrons can flow, and then you will essentially deplete some of the excess charge here, and so more zinc can be dissolved off. And this can supply a continual potential difference, and that potential difference just depends on the different constituent chemicals involved. As long as there's more zinc to dissolve, eventually you'll dissolve all the zinc, and you won't be able to. Your battery would be dead then. Okay. And by the way, a single battery like this is actually called a cell. I shouldn't call it a battery, even though we do. What Volta found is that if you combine a bunch of cells into what he called a battery, just like you can have a battery of cannons, it just meant like a whole bunch of things. He also called it a pile, which is still the word they use in French for battery. They call it un pile. Anyway, if you combine a bunch of those, then you can increase the voltage, because if you just have a single cell, the voltage is set depending on the chemicals involved. So now we can look at the idea of a circuit. In order to have a circuit, you have to have a complete loop, as is shown here. The reason for that is the charges can't just pile up in one location. The charges, in order to flow, they have to come back to where they started. Now the battery essentially gives them an additional push. It gives them more energy to keep them flowing, but you can never just have a battery and a wire that isn't connected to anything, because the charges aren't going to just jump off the end of the wire. Unless you get a huge voltage, I guess, then you can get sparks, but typically that's not going to happen. Also, what we call current, which is the flow of electricity, we define it as, we use the symbol I for current, I'm not sure why, but we define it as the change in charge, or the number of charges flowing, the amount of charge flowing, measured in coulombs per time. So this is going to be coulombs per second, and we redefine a new unit. We call it the ampere, or amp for short, and the symbol is just an A, also named after a French scientist. And 1 amp is equal to 1 coulomb per second. So a current of 1 amp is a fairly good current. Okay, and the direction of the current, what we call conventional current, when we solve for I, we're going to be talking about conventional current. This was chosen more or less at random before we knew anything about electrons. I believe it was actually Benjamin Franklin who chose the direction away from the positive side to be the direction of current. So the electrons are actually flowing the other way, but in most all situations, negative charges flowing one way are identical to positive charges flowing the other way. So it doesn't matter too much, though it would have been nice to have the things that are actually moving be used to define the direction of current, but alas, we are stuck with the history of these things. Alright, we could also find instantaneous current. You probably guessed it by doing dq dt if we wanted to look at that. So this would be the average current over that time interval. Let's look at a pretty basic problem here, but just to get our feet wet. We want to know how much charge will pass by a given point if we have that current for that amount of time. So we have I equals delta Q over T. If we rearrange that to solve for delta Q, because that's what we're trying to find, that's the charge that passes a given location, then we're going to have the current times the time. Our current is 2.5 amps, but amps are coulombs per second, and this is in minutes, so we're going to have to convert those minutes to seconds, which is easy enough to do. Anyway, we get 600 coulombs of charge past that point during 4 minutes. If we're interested in how many electrons that would be, we just need to divide the number of coulombs by the charge on one electron, which is 1.6 times 10 to the negative 19th. And that gives us a whopping 3.75 times 10 to the 21st electrons. So there's a whole lot of electrons involved when you have electrical currents flowing. Alright, next thing we need to look at is what is called Ohm's law. This guy was a German scientist. His name was George Ohm. And what he found was that the current was directly proportional to the voltage. Might not seem that historic today, but he got a law named after him. It's actually not a law, but we call it that anyway. And we decide that the constant of proportionality here, we're going to call that the inverse of the resistance. So this is a new quantity here, electrical resistance. And it has units of ohms. And the symbol for ohms is a Greek capital omega. or maybe that's lowercase. Either way, looks like that. Okay, so we have this new definition here. Often it's rearranged. Probably the most common form is V equals I times R. You might have heard of this guy. That's called Ohm's law right there. Now, the reason why it's not a law is because it doesn't actually hold for everything. For some materials, we don't get a linear relationship between current and voltage. We get our current increasing at an increasing rate as we increase voltage. And in this case, we would just say, oh, it's a non-ohmic material. Beautiful, huh? And if it's an ohmic material, then it follows Ohm's law. Otherwise, it doesn't. But most things, most normal, circuit components, electrical wires and whatnot, are ohmic. So we're not going to see a whole lot of this. But if you're an electrical engineer or something, you'd have to deal with those types of things. All right, the symbol for a resistor, since we now have to deal with resistance, which you might have guessed, it's kind of what impedes the flow of current. It's just a squiggly line like this. So if we have the current flowing this way, what happens when you go across this is you lose some of your potential. The current over here has to equal the current over here because that's the flow of charge, and you can't have more charge flowing here than here, otherwise you're going to get an excess of charge building up somewhere. But what happens is the charge over here is at a lower potential. Essentially, you lost some of the energy in those charges, even though the total number is the same, when you cross over a resistor. So let's look at a fun little animation for a second. Alright, so here we have a simple electrical circuit. Here I've got my battery. I've got these little winged angel thingies, I don't know what. That's essentially like the electrolyte that is that's carrying the charge from the cathode to the anode, or maybe vice versa, I forget. Anyway, but that's creating a potential difference on our battery, and that's causing current to flow, charges to flow. Here, this big red thing up here is our resistor, and so essentially the charges bump into these atoms and get slowed down. Over here I've got a pinwheel apparently measuring my current. A meter that measures current is called an ammeter, by the way. There's no P in it. It's not an amp meter. It's an ammeter. So as I increase my resistance, you'll notice I've got more things to collide with here. My current slows down, but I still have the same number of charges. I just end up with more charges building up over here than over here. But if you notice, the rate at which they're flowing is actually the same on both sides. You have to have the same current throughout, as I mentioned earlier. Okay, so one more pretty quick, easy example. If we have a flashlight that draws 300 milliamps with a 1.5 volt battery, we can use that to find the resistance of the bulb just by using V equals I times R. So if we solve that for R, we get V over I, and then we can just plug in 1.5. Now if we want resistance in ohms, we need voltage in volts and current in amps, not milliamps. So we're going to have to divide that by 1,000 and make it 0.3. So that's going to give us a resistance of 5 ohms. Now the resistance is a property of the light bulb or the material that the light bulb is made of. So it doesn't change as you change V and I. It would change as you change something about the light bulb. So otherwise you double V, you're going to double I. You're not going to affect R. Similar to what we saw with capacitors. Changing the voltage changes the charge on a capacitor, doesn't change the capacitance value. So here for the second part, which should be labeled part B anyway, if the voltage goes down a bit because our battery is getting old and dying, that's not going to change the resistance in the light bulb, but it will change the current. So we can plug back into this equation, but now using a different voltage. I guess if we rearrange this to start with, we're going to have the new current equals V over R. So our voltage dropped a bit, our resistance is still the 5 ohms, and we're going to get a 0.24 amp current, which is equal to 240 milliamps, just to compare it to our original 300. So our current went down a little bit. Alright, now on to yet another kind of silly vestige of history. what is called the resistor color code. So back when they started making resistors, they didn't really have the capability of printing nice, neat, small numbers on these things, but they were able to print colored bands, and we still use this quite a bit today. You'll find some resistors that have the value just printed on there. They might say 200 ohms or something like that. But it's very typical to find these colored bands here. And it's a code, and here is the key to the code. Each color represents a different digit, and then depending on the placement of the color, you're going to have 2 digits for your value of your resistance, and then the third one is going to be the power of 10, and then this whole thing is going to be ohms. Tolerance is basically how accurate the measure is, so that's over here. If it's got a gold band there, it means that the value listed by the first 3 multipliers is accurate to within 5%, and otherwise it's less accurate than that. And you can buy resistors that are more accurate. You can buy like 1% precision resistors up here with a really good tolerance. So let's look at the resistance of this resistor here. So the first digit is red. We come to our decoder ring over here, and red is the number 2. The next one is green, so we come to our decoder and we get a 5. And that's not a negative sign, that's a fill in the blank there. So yellow is our multiplier, and we come, so we get 2.5. Sorry, it's always a decimal implied there. So you get 2.5 times 10 to the 4th, which is 25,000 ohms, which is actually not that huge of a resistance. You get resistance in the mega ohm range. That's not uncommon, but you can have really small ones too. You could have a 5 ohm resistor or a 1 ohm resistor. In order to memorize this nice little random ordering of colors here, there are a number of different mnemonic devices. Here are some. You can pick your favorite, so this just helps you remember them in order. So big boys race are young girls, but violet generally wins. Tells you, now it's a little tricky because you've got a couple of B's in a row, but it starts black, brown, I believe. Let's double check. Yeah, black, brown. So I don't know how you remember that, but anyway, black, brown, red, orange, yellow, green, blue, violet, that one's easy, green, and white. So I might have got the G's switched too. So anyway, you probably just want to look it up on a table unless you're going to be an electrician and have to use this all the time or something. Okay, I will see you next time. That's all for today.